All right, guys, welcome to Lesson 3 of Unit 5. We're going to talk about something called the mean value theorem. It's another pretty important theorem. Definitely will see it somewhere on your AP exam. Like all theorems, it has some hypotheses that have to be met first. Like when we did the extreme value theorem, for instance, it had to be continuous, right? Well, mean value theorem has some requirements too. We'll look at that. So we'll also be able to tell when and if you can even use this theorem. And then after that, we're actually going to go ahead and apply the theorem and do some problems. Okay? So let's go ahead and start off, first of all, by talking about what the mean value theorem is. So let me draw a function here. Let's say it looks something like this. Right? And we have these two endpoints here and here, and we'll go ahead and call this point here A, which means that the y value would be f of A, and this x value we'll say is B, which means that the y value is f of B. Of course, I'm assuming the function is f of x, right? That's why I'm using the letter F here. All right, so first of all, I want to ask you guys to try to remember a couple of things. Now, first of all, if I were to ask you guys, how do you find the average rate of change of this function on this interval? How do we find the average rate of change of this function on this interval? The average rate of change on this interval, which is A to B, can be found by finding the slope of your secant line. Okay, so do you guys remember what a secant line is? What is a secant line? A secant line is a line that connects your first point to your last point. A straight line. And the slope of that line represents the average rate of change. So how do we find the slope of that line? Well, we do the old school y2 minus y1 over x2 minus x1 formula, right? So it's going to be f of B minus f of A over B minus A. Okay, so that's the average rate of change of that function on the interval from A to B. Now the next thing I'd like you to do is, and hopefully if you guys are writing these notes down, is using a pencil, not a pen, just in case you're wrong, but pause the video here and see if you guys can draw a tangent line. Now you got to remember, a tangent line is a line that will touch this curve only once. Okay, it doesn't go through 2 points, but it's going to touch the curve once in between those 2 points somewhere. But I want you guys to draw a tangent line somewhere on that interval. But I want that tangent line to be parallel to the secant line. So I want you guys to sketch a tangent line that is parallel to the secant line. All right, so I'm going to go ahead and do that right now. And I would say that that would probably happen like right about here-ish. Those two lines are pretty much parallel, right? So that's a tangent line. Now, what does the slope of a tangent line tell us? You guys remember what a slope of a tangent line tells us? The slope of a secant line tells us the average rate of change. The slope of a tangent line tells us the instantaneous rate of change. And it's not on an interval like the average is. The average is the average from A to B, but an instantaneous rate of change happens at a single point, which we'll say here is at a C value of X and a Y value of C. Okay, so that's the instantaneous rate of change, not on an interval, but at a specific point of x equals c. Okay, so there's that. Now, how do you find the slope of your tangent line at that point? How do you find the instantaneous rate of change? Well, instantaneous rate of change is the derivative of your function at that point. Now I want you guys to think back to geometry for a second here. But before we do, let's review. We have instantaneous rate of change at a single point represented by the slope of the tangent line. We have average rate of change over an interval represented by the slope of the secant line. Now let's think back to geometry for a second here. What do we know about parallel lines? We know that their slopes are equal. So I asked you guys to make two parallel lines, which means that the slope of the tangent line would have to be equal to the slope of the secant line. And by the way, in case you forgot, we can add this to our picture. Put little arrows on here. That indicates that the lines are parallel. So that means the slope of my tangent line is parallel to the slope of my secant line because they're parallel. And if you didn't remember that, you might want to write that down. Parallel lines have the same slope. All right. So if the slope of the tangent line is equal to the slope of the secant line because they are parallel, that means the instantaneous rate of change at x equals c is equal to the average rate of change on the interval. Okay? If the instantaneous rate of change is equal to the average rate of change, that means that f prime of c would have to be equal to f of b minus f of a over b minus a. Now, what we just did here was we found the point in time at which the instantaneous rate of change is the same as the average rate of change. Okay, so a good way to think about this is like, let's say you're driving to Las Vegas or something like that, right? And on your way there, you're going to stop, you're going to start, you're going to pick up some food. Sometimes you're going to go fast, sometimes you're going to go slow, depending on the traffic. So your speed is constantly changing. But in the end, if you want to find your average speed, you're basically going to take how far you traveled and divide that by the amount of time it took. Okay? You're going to ignore all the starting and the stopping. You're just going to look at the total distance over the total time. That's going to tell you your average speed of the car. All right? Now, let's just say you did that and you found your average speed was 40. Well, that's what would be represented by the slope of this red line here. That's the average speed of your car, the total distance over the total time. But what's represented by this green line here is at what points in time on the trip did your car actually reach that speed of 40 miles an hour? So in other words, you're looking at the specific points in time at which the instantaneous speed is equal to the average speed. Okay? And so there it is. That's going to be the bedrock and the foundation of what we're talking about today that leads us into this thing called the mean, which is another word for average, the mean value theorem. Okay? So now before we get into the mean value theorem and its details, I want to point out a couple things. There are some requirements. Okay? First of all, the endpoints have to exist. If the endpoints don't exist, then this doesn't exist, right? You have to have the endpoints exist. You can't have open dots on the endpoints. Second of all, you can't have any holes, gaps, or jumps on your curve. Because what if this was the one point right here where the tangent line would have been parallel, but it just so happens that at that point there was a gap? Well, now you just lost it. That point doesn't exist anymore. So your function has to be continuous on a closed interval. You can't have any holes, gaps, or jumps, and the endpoints have to exist. Finally, since we're trying to find the slope of a tangent line, obviously then, for every point along this curve, you would need to be able to find the derivative at every point along the curve. Okay? So you can't have any places where the function's not differentiable. The function has to be differentiable on the entire interval. Okay? So there's two requirements for this possibility to work. It has to be continuous and differentiable. All right? Now, just so you guys know, another fact is that sometimes there could be more than one. Let's say that my function looked like this instead. Still the same 2 points. We'll call them A and f of A. And we'll call it B and f of B. But I'm going to connect these two dots in a different way this time. Instead of just connecting them like this, you could connect these dots like this, couldn't you? I mean, it just depends on the function, right? Whatever your function is. Now, let's just say technically it would have the same average rate of change. But what that's going to do is that's actually going to increase the number of possibilities we have for parallel lines. So let me, there's my secant line, right? But this time, if I asked you guys to draw a tangent line that's parallel to that red line, you actually would have 3 possibilities. You could draw one here. You could draw one here. Probably more like right here. And you could draw one here. Oop, that's not parallel. Probably more like right here-ish then. Okay, so my point in pointing this out to you guys is that so long as you have a continuous and differentiable function, there is going to be at least one, if not more, places where the instantaneous rate of change of your function is equal to the average rate of change of your function. And that's the mean value theorem. So now that we've kind of talked about it, let's go ahead and be a little bit more specific here. All right. So if a function is continuous on the closed interval, no gaps allowed, and differentiable on the open interval, no cusps allowed, then there is a value C between A and B where the instantaneous rate of change would equal the average rate of change. In other words, there's a tangent line at x equals c that's parallel to the secant line between A and B. Or you could also think of it as c is the point at which the instantaneous rate of change is equal to the average rate of change on the interval A to B. Now I want to point out to you guys, this is just a summary of everything I've already said, but it's just more formally stated. So this only works provided that it's continuous and differentiable. But basically the mean value theorem is a theorem that tells you that a point exists. Okay, it means that somewhere there is a c value where the derivative at that point will be equal to the average rate of change. That's what it tells you. Now you guys might be thinking, well, who cares? Why would anybody care about that? Well, we'll get to that in a second. But for now, just know the mean value theorem just tells us, yes, there is a point that exists. It doesn't necessarily tell you what the point is. It's like the extreme value theorem did the same thing. The extreme value theorem didn't tell us what the absolute max and min was. It just told us that it existed. Well, the mean value theorem does the same thing. It doesn't tell you at what points these things happen, but it just tells you that they do in fact exist. Now, we can do some algebra to find those points, but the mean value theorem just tells us that it exists. But in order for it to work, once again, you have to have these criteria up here satisfied. It has to be continuous on the closed interval, meaning the endpoints have to exist. Might want to add this, endpoints necessary. And it has to be differentiable on the open interval. Now, that means you can't have any cusps. You also can't have any vertical tangent lines. Vertical tangent lines also are a place where a function is not differentiable. So you can't have any cusps, and you can't have any vertical tangent lines. If you do, then we can't use the mean value theorem to be sure that there is a c value where the derivative equals the average rate. Okay? Why? Because if a function is not differentiable, then this might not even exist. So if that doesn't even exist, how could it possibly equal this, right? So it has to be differentiable. But you might notice that it says on the open interval. In other words, we're not looking for the slope at the endpoints. Endpoints are not necessary for differentiability. So for continuity, the endpoints have to exist. But after you take the derivative, it doesn't matter if the endpoints work on the derivative or not. We don't care about the endpoints for the derivative. We only care about the endpoints for the original function. So continuity has to do with whether those endpoints exist on the original function. Differentiability, we don't care if the endpoints work on the derivative. Okay, so we'll kind of play that out as we do a couple of examples, but there you go. All right, so that's the mean value theorem. It's just basically a theorem that tells you that yes, somewhere there's a tangent line that's parallel to your secant line, and then we could do some algebra to find out exactly where that is. So now you might be wondering, that seems kind of weird and obscure. Why would anybody even care about that? Well, it turns out that theorem, although it just seems kind of like, well, why would anybody care about that in and of itself? Well, it's not immediately obvious, but it turns out this theorem is actually very crucial in quite a few different circumstances. As you guys can see, we did this earlier this year. Remember when we found the limit of the difference quotient and it gave us the derivative? Well, if you just look at this piece right here, that looks exactly like what I wrote on the last page, doesn't it? Earlier this year, too, in Unit 2, we learned about the fundamental theorem of calculus. Believe it or not, that somehow this also has something to do with the mean value theorem. So the mean value theorem, basically, why is it so important? Because it provides the backbone for these are both major concepts in calculus. The mean value theorem provides the backbone for a lot of the major theorems that exist in calculus. So that's why we care about it. It's kind of not useful in and of itself, but it's very useful for the heart of calculus. Okay? All right, so let's talk about how to use the mean value theorem, what we're going to do with it today. So I'm going to start by giving you guys a function, okay? And the first thing you need to do is you need to make sure that it is differentiable and continuous on the intervals that we care about. And I think I want to change this little sentence up here. And you guys should probably do this with me on your notes. So the first thing we want to do is we want to ask ourselves, does the MVT apply? That's really what we're trying to do there. And then as a side note of that, we need to see, is it continuous on AB with the endpoints included? And then we need to see if it's differentiable on AB. Okay? So that's really the first step there. I think I'm going to go ahead and change these bullets here to numbers as well. All right, so there we go. So we're going to first of all see, does the MVT apply? That means, is it even worth looking for? Is there going to be a point on that curve where the instantaneous rate of change is equal to the average rate of change? And to do that, we check these two things. After that, we're going to go ahead and find f of b and f of a and plug it into this average rate of change formula. Then we're going to find the derivative, and we're going to set the derivative equal to that average rate, and then we're going to solve for x, and that will tell us that point where the instantaneous rate of change actually comes out to equal the average rate of change. Okay? So let's go ahead and we'll do our first example here. All right? If the MVT can be applied to the given function, find all the values for which, or I should say find all the values of C for which the instantaneous rate of change is equal to the average rate, or this little formula right here. So let's go ahead and begin. I've given you a function and I've given you an interval. All right? So just to kind of bring it to life a little bit, we have a picture. Now we're not going to be using the picture very much, honestly, but so here's the function x squared minus 3x plus 2, and we're going from x equals 1 to x equals 4. Okay, and just to kind of explain what we're doing, we want to find the secant line's slope between those two endpoints, and then our goal is going to be to find the value of x at which the instantaneous rate of change is equal to the average rate of change. In other words, we end up with parallel lines. And as you guys can see, it looks like it's going to be somewhere in between 2 and 4, which means we could probably guess it might end up being a nice number like 3, but it might not. So, but there's the idea. All right, so let's go ahead and begin the process. So I'm just going to be going through these steps here, and so follow along with me. So step 1, we want to make sure that the MVT actually applies. Okay, well, we have to check two things. We need to make sure that it's continuous on the closed interval, 1 and 4. And then we also need to make sure that it's differentiable on the open interval. In other words, we don't really care if it's not differentiable at the endpoints, but it has to be differentiable everywhere else in between. All right, well, how are we going to know that? Well, once again, we start by just looking at our functions. Since f is a polynomial, it's continuous everywhere. Okay, so that takes care of that. And is it differentiable? Well, to know that, we need to find the derivative first. So let's find the derivative, f prime of x. What is the derivative of f of x? Well, it would be 2x minus 3. And that's also a polynomial. So since f prime is a polynomial, it is also continuous everywhere. And if the derivative of f is continuous everywhere, that means that f is differentiable. Okay, so if the derivative is continuous, that means that the function is differentiable. And it's actually differentiable everywhere. So it is differentiable at the endpoints, but we don't care about those for differentiability. We just want to make sure that it is, in fact, differentiable, at least on the open interval, and it is, because it's actually differentiable everywhere. So there it is. So that's the first step. You want to make sure it's continuous, and since it's a polynomial, it is. And you also want to make sure it's differentiable, and since its derivative is continuous, then yes, the function is also differentiable everywhere. So that means that somewhere on the interval from 1 to 4, there has to be a specific point in time at which the function's instantaneous rate of change is equal to its average rate of change. So we know that our searching now is not going to be in vain. It's going to be a worthy cause. So let's move on to step 2. Step 2 asks us to calculate f of b minus f of a Okay, so to do that, we need to start out by knowing what our a and b are. My a and b are 1 and 4. So I need to start by figuring out what is f of b. F of b in this case is going to be f of 4. And that just means I'm going to plug 4 into my function up there. (16 minus 12 is 4 plus 2 is 6. So there's f of b. Now I need to find f of a, and since a is 1 in this problem, we're going to be plugging 1 into our function. 1 squared is 1, minus 3 is negative 2, plus 2 is 0. So f of a would be 0. So then plugging all this stuff into my little formula here, we just found out what f of b is. F of b was 6. F of a was 0. B was 4 and A was 1. And so I end up with 6 over 3, which is 2. So my average rate of change is 2. In other words, the slope on the interval from 1 to 4 is approximately up 2 over 1. Rise 2, run 1. Okay? So there is step 2. Now step 3 says find the derivative. We already did that, but I'll do it again. The derivative was 2x minus 3, right? Now step 4 asked us to set the derivative that we found in step 3 equal to the average rate of change that we found in step 2 and asked us to solve for x. So for step 4, we're going to take our derivative and we're going to set it equal to what we got for f of b minus f of a over b minus a. Okay, so my derivative is 2x minus 3. And f of b minus f of a over b minus a, we figured that out in step 2 and we found out that that was 2. So now I can solve for x. But before I do, let's not forget what we just did. The instantaneous, I'm trying to find the value of x at which the derivative is equal to the average rate of change. So my derivative has now been set equal to my average rate of change, and I can solve for x. That will tell me the point in time at which this function has an instantaneous rate of change that is equal to its average rate of change. So start by adding 3 on both sides. Remember how we said that it would be somewhere between 2 and 4? And we said, well, maybe it's 3, but maybe not. Well, it's not quite that. It's 5 over 2, which is 2.5. So that is the point on our curve where the tangent line is parallel to the secant line. Okay, and so going back to our original problem here, or the graph, I mean, so 3 would be like right about here, 2.5 would be like right about here. So I would say that that tangent line, which is parallel to this secant line, would be right about there. Okay, and so there's our final solution. All right, so let's do a guided practice. Why don't you guys go ahead and pause the video here and do step 1, please. And when you unpause it, you will see the solution. Okay, so does the MVT apply? Well, we got to see, is it continuous on negative 1, 1? Yes, once again, it's a polynomial, so it's continuous everywhere. Is it differentiable on the open interval negative 1, 1? Once again, the answer is yes, because the derivative is also a polynomial. And if the derivative is continuous everywhere, that means the function is differentiable everywhere. So does the MVT apply? Yes. That means that somewhere on the interval from negative 1 to 1, the average rate of change is equal to some derivative, or there is a value of x at which the derivative is equal to the average rate of change on that interval. So we're not going to be searching in vain. All right, go ahead and pause the video here, please, and do step 2. All right, so here's the step 2. B is equal to 1, and A is equal to negative 1. And so f of b is f of 1, which is 1 to the 6th, which equals 1. And f of a is f of negative 1. Plugging that into our function, we get negative 1 to the 6th power, which is also 1. And so plugging it in up here to our difference quotient, we have 1 minus 1 over 1 minus a negative 1, which gives us 0 over 2, telling me that my average rate of change is 0 on that particular interval. All right, go ahead and pause the video here and do step 3. Step 3 we've already done. It's a redundant step. You have to do step 3 way back in step 1 anyway, which is to find the derivative. The derivative is 6x to the 5th. We already did that though, so whether or not you want to actually include step 3 in your process, you just draw an arrow to it or whatever, it's redundant. But now we get to move on to the fun stuff. Let's go ahead and do step 4. So pause the video here and do step 4. And when you unpause it, you will see the solution. Right, and so Step 4 is to set the derivative equal to the average rate of change, which is 6x to the 5th equals 0. And solving for x, if you divide both sides by 6 and then take the 5th root, you end up with just the fact that x equals 0. So this graph, if you were to graph it, it would look something like this. And we're going from -1 to +1. And so the secant line has a slope of 0. Well, the tangent line is parallel. That would happen right here at the base, and that would be parallel to that at x equals 0. Okay, so that's a guided practice. Now I want you guys to try one completely on your own from beginning to end. So go ahead and pause the video here and solve this problem. Now, when you guys get to the last step, solving it will require some algebra skills. But just do your best. Go ahead and go as far as you can with it and see what you guys get. When you unpause it, you'll see the entire solution. Okay, so hopefully you guys didn't have any trouble at least getting this far. After that, we got to solve it. So now to solve it, I'll work that one out live with you guys here, just because it's a little bit, trickier than the ones that I was doing with you earlier. That. Now that's a quadratic equation. Now when you have a quadratic, you can either do the quadratic formula or you could try factoring. I like factoring personally, but unfortunately sometimes factoring doesn't always work. I'm going to hope that factoring works, and I'm going to try it. But if it doesn't, we might have to be stuck with the quadratic formula. So let me try to factor this really quick. See if it works out. That would be 3 and 2 makes 5, so that's no good. 6 and 1, that's not going to work. Okay, unfortunately this thing is not factorable. So if it's not factorable, then you can't factor it. I like factoring because then you just set each factor equals 0 and solve. At this point, what you would do is you would use the quadratic formula. And sometimes you got to do that. Okay, so that's where we do x equals -b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so my b is -6. My a is 3, my c is 2. (36 minus 24 would be 12. Now, there's two answers there. I wonder if they both apply, because we only want answers on the interval (0 to 1). Okay. Now, if you want to calculate these things, you would have to do 3 plus the square root of 3 over 2 and 3 minus the square root of 3 over 2. So I'm going to do that really quick on my calculator. I'm pretty sure they both work, though, and the reason I think they'll both work is because the square root of 3 is less than 3. So whether you add or subtract it from 3, you're going to end up with a positive number. But maybe we might end up with one that's too big, and therefore it will be outside of our range. So one of the answers is 2.3. Then we have 3 minus the square root of 3. And the other one's 0.6. In calculus, we're supposed to go up to 3 decimal places, so let me do that. I didn't do it here, but that's okay. This number here is not in our interval, right? It's outside of the interval from 0 to 1, so we could ignore that one. So my answer is 0.634. Okay. So unfortunately, sometimes you do got to do the quadratic formula, but don't forget to make sure. This is actually a pretty important note. Make sure that your answer is actually on the interval that we care about. Now, step 1 guarantees that you should have at least one answer on that interval. But so if you only get one answer, then that's your answer. But if you get 2 answers, like in this case, you better check both of them, because one of them might be on the interval, which is what step 1 promised, but the other one doesn't have to be on the interval. Okay? So draw a little arrow from this statement to that, and that'll explain why we crossed it off. And the final answer is 0.634. All right, so that's the mean value theorem. Tomorrow we're going to do more of the same thing, but we're just going to do it with more complicated functions. But this is a really important theorem, so I wanted to make sure we start off with something kind of easy, get you guys really used to it, so that you're not baffled by the things that are coming up later. So the rest of our lesson, we're going to look at explaining why the mean value theorem doesn't apply, because there will be some problems where that comes into play later on. So let's begin here. Why does the mean value theorem not apply? Well, if we just follow the steps, we'll see why. The first thing we need to do is we need to check, is it continuous on the closed interval -3 to 3? And we also need to check, is it differentiable on the open interval -3 to 3? Okay, so now on all the problems we're about ready to do on examples 2, 3, and 4, I think, it's going to fail. It's not going to work. We just have to figure out why. All right. So let's start off with, is it continuous? Well, this is a rational function. Rational functions have discontinuities anytime the denominator equals 0. So if x minus 1 equals 0, that means x equals 1. Now, that number is on the interval. And so there's our reason. So since the function has a discontinuity at x equals 1, which is on the interval -3 to 3, MVT does not apply. Now, remember, that doesn't mean that there isn't an answer. It doesn't mean that there's not a point where the instantaneous rate of change is equal to the average rate of change. It just means that we can't be sure that it exists until we actually go through and give it a try. Okay? Now, since it's already failed with our first test, we're not going to even worry about this. That's irrelevant. We don't need to. If it's not continuous, then we're good. All right, let's go ahead and move on to another one here. Explain why the MVT does not apply here with this function on this interval. Well, we want to see, is it continuous on -3, 10? And we also want to see, is it differentiable on the open interval -3, 10? That's the question. One of these is going to fail, and we're going to see which one. Okay, well, x minus 5 is a polynomial, so it has no discontinuities. So when you take the absolute value of that, it has no discontinuities either. So and why doesn't x minus 5 have any discontinuities? Because it's a polynomial. X minus 5 is a linear function, which is a type of polynomial. And when you take the absolute value of a polynomial, that's not going to all of a sudden cause it to not exist somewhere. It's just going to make all the answers positive, but it doesn't make it not exist. So absolute values typically in that case are not going to affect the continuity. But let's go ahead and see if it's differentiable. Well, now we already know it's going to fail in this way because I told you it's going to fail, so it didn't fail the first way. It's got to fail the second way, right? But we still want to work it out and show it. Okay, so to do that, then we need to find our derivative. Now you need to remember how to find the derivative of an absolute value function. The derivative of an absolute value function is whatever's on the inside put over the original function itself times the derivative of the inside. The derivative of the inside is 1. So there's my derivative. Now when I look at this, does this have any discontinuities? Well, now that it has a denominator, the answer is yes, it does have a discontinuity. It has a discontinuity if the absolute value of x minus 5 equals 0. Now that's only going to happen if x minus 5 equals 0, which would happen if x equals 5. So at x equals 5, we have a discontinuity. All right, so we would say that MVT cannot be applied. Since there is a the function is not differentiable. Notice I'm not going to say it's not continuous because it was continuous. It's not differentiable at x equals 5, which is on the interval -3 to 10, right? 5 is in between those two numbers, so we're good. Now, just so you guys know, if you ever end up with a discontinuity, like let's say we did this process and I got a discontinuity at 10, that would be okay because we don't care about the endpoints. We just can't have any discontinuities in between those two values when we're checking for differentiability. All right. Explain why the MVT does not apply here. Well, looking back at our little sheet about the continuity of common functions, cosine is continuous everywhere, so that's fine. But tangent is not continuous anytime you have pi over 2 plus some multiple of pi, okay? So this tangent is not continuous at pi over 2, which is on the interval. Okay, oops, I wrote that wrong. So tangent has a discontinuity at pi over 2. And if you want to look at your unit circle, we start at 0 and we end at pi. Pi over 2 is up here. And tangent is undefined at this point. So as I'm going from 0 to pi, tangent has a discontinuity on that interval. Now you can also know it by looking at your little worksheet that tells you the continuity. Tangent is discontinuous at pi over 2 and any multiple of pi that's added to it after that. Now since it's already been proven that it's not continuous on the interval, then we're good. So since tangent's not continuous on the interval, then that means this whole thing's not going to be continuous, because if you add something that doesn't exist to something that does exist, it still ends up not existing. So the MVT does not apply since the function is not continuous at x equals pi over 2, which is on the interval. Now you guys are noticing that I keep saying which is on the interval, because if you find a discontinuity that's not on the interval, then it doesn't matter, because we only care about the interval that they're asking about. So if you end up with a discontinuity outside the interval, we just don't care. We only care about those discontinuities that are actually on the interval. All right, so those are some situations where you would not be sure that if you went through that long process of trying to find that point where the tangent line equals the secant line, you can't really be sure you'll actually end up with an answer. You may not end up with an answer. All right, last example here. So like these last two examples I'm going to do with you guys here are probably the most important ones for the day, at least for your AP exam. So pay close attention to these guys. The table below gives selected values of the differentiable function g on the interval from 0 to 10. Can it be shown that there's a value c such that g prime of c equals 2 on 0, 8? So what makes this problem different is we're not going to find, we're not going to actually find the value of x where that happens. We just want to prove that it exists. Okay? So first of all, they tell us that the function is differentiable on the interval 0 to 10. So since g is differentiable on the interval 0 to 10, we know two things, okay? We know, first of all, that it would have to be differentiable on the open interval. Why? Well, these two things are exactly the same. This one just has more. So if it's differentiable on the closed interval, it has to be differentiable on the open interval. And we also learned back in Unit 4 that if a function's differentiable, then it's continuous. So since g is differentiable on 0, 10, it's also continuous on that interval. If a function's differentiable, then it has to be continuous. We learned that back in Unit 4. So that alone tells us that we can apply the MVT to this table, but it doesn't tell us that it has to equal 2. So we have a little bit more work to do. But we do know that we are allowed to apply the mean value theorem to this table, okay? Because they told us it's differentiable. All right, so we're going to move on to step 2. Step 2 is we know that since the mean value theorem applies, we could say that g prime of c is equal to g of blank minus g of blank over blank minus blank. And what's our blanks? It's right here. Now, some of you guys might wonder, why isn't it this? Well, the one that they give you in the question, that's the one you're going to use. So I want to prove that the average rate of change on this interval from 0 to 8 is the one where the average rate of change is 2. So it's going to be g of 8 minus g of 0 over 8 minus 0. Now g of 8 is 11. G of 0 is negative 5. That's going to be 16 over 8, which is 2. Done. All right, so you have two things that you need to do with these table problems, okay? First of all, you need to say, okay, well, since it's differentiable, it's continuous and differentiable on the intervals that we care about. Now, on number 2, you're actually going to do the math, though. And you're going to apply it to the interval that's in the question. And therefore, I've proven that, yes, there has to be some value c where the derivative equals the average rate of change on this interval. And the average rate of change on that interval happens to be 2. So we've proven it. Yes, there is a value c such that g prime of c equals 2 on that interval. So there's your 2 steps. Okay? So it's a little bit less work than the other one because you don't have to find a derivative and you also don't have to solve for x. You just need to do these 2 steps and you'll be good to go. All right? Now, let me move you guys up here. I want you guys to do 2A for me, please. So pause the video here and do 2A, and when you unpause it, you'll see the solution. Don't do 2B yet, but do 2A. And when you unpause it, once again, I'll show you the solution. All right, so there's the answer to A. I'll let you guys study it and see what you think. Now, I don't want you guys to solve B yet, but I want you to take a look at B. What do you notice about the question in part B? Compare your question in part B to the question in part A. There's a very important difference, and it's not just in the numbers I gave you. It's a very subtle difference, though. Do you guys see the little difference? On part B, I'm just asking about h, but on part A, I'm asking about the derivative. Why does that matter? This is not a mean value theorem question. This is an intermediate value theorem question, something that we learned back in Unit 3. So I'm talking about this and I'm reviewing that with you right now because they look so similar. They look almost identical, these questions, and yet they're completely different theorems. Okay? If you're asking, does a derivative exist, that's a mean value question. If they're asking, does a y value exist, that's an intermediate value theorem question. So I want to review how to do that with you guys really quick, and then I'll have you do part B. So how do we do the mean value theorem? So in example 5b, you'll notice here that I'm not asking, is there a derivative that equals 2? I'm asking, is there a y value that equals 2, which is an IVT problem. Okay, so you might want to draw a little area that it's IVT, whereas on the last slide, maybe go back to it and we'll put MVT. Okay, so let's go ahead and review how to do the IVT. All right, how does the IVT work? Well, let's just first of all review what it is. The IVT tells us that if I'm going from point A to point B, so long as that's a continuous line, somewhere along the way I've got to cross point C. That's what the intermediate value theorem tells us. But it has to be continuous. So, step 1. You got to make sure it's continuous. Otherwise, the IVT doesn't apply. So, since G is differentiable, it's continuous. The next thing we need to do is we need to prove that we're going from point A to point B. So here's my A. Actually, take that back. Here's my A and here's my B. Okay? So let's find out what f of B is first. F of B would be f of 8, and f of 8, not f, I'm sorry, we're doing G. Let me change those letters. We don't want to get that wrong. G of B is G of 8, and G of 8 is 11. G of A would be G of 0, and G of 0 is negative 5. So we're going from 11 to negative 5. The next thing you need to make sure is you need to make sure that this value, your K value, is in between those two things. Is 2 in between 11 and negative 5? Yes. So then we get to say our fun little statement. Since G is continuous and goes from 11 to negative 5 on the interval 0 to 8, there must be some value C for which G of C equals 2. Okay, so that's a review question from way back in Unit 3. And the reason why I want to review it once again is because it looks so similar to the types of questions that we're doing today, but they are different, and it all has to do with whether or not you're looking at a normal function or a derivative. So just to kind of keep that fresh in your mind, why don't you guys go ahead and practice part B here. Pause the video, and when you unpause it, you'll see the solution. And I just realized there's a typo there. We want to make sure that this is a negative 4. So make sure you make that a negative 4. So once again, since the function's differentiable, it has to be continuous. Then we identify our A, B's, and C's. H of B is 9, H of A is 3, and we want to make sure that our C value is in between those, which it is, and then we make our statement. So since my function's continuous and it goes from a y value of 9 to a y value of 3 on the interval from negative 8 to 4, then it's somewhere along the way it has to cross a y value of 5. So there has to be some C value such that when you plug it into your function you get a y value of 5. And so that's the intermediate value theorem. It looks a heck of a lot like the mean value theorem. They only differ by a little apostrophe, but they mean completely different things. And so worth reviewing so that we can distinguish the two. All right, and that does it for our lesson for the day, and we'll see you guys next time.